Okay, so this is looking at how machine learning can be applied to the area of electronic trading. The first thing we have to understand is that electronic trading is quite a complex area. You can think of it as an ecosystem where you have different entities making decisions at the investment level, and then at the trader level, trading desks are decomposed into various functions, from selecting the trading strategy, the trading venues, routing. There's lots of information that is fed into the cycle. Plus, there are many entities that are analyzing the data. So because of that, there are many forces that are reshaping the sector. So something called deverticalization means that the traditional entities are being broken into services, and alliances can be formed, and new players, like we have seen in the payment system, the Google and the Apple getting into the payment space. So the same thing is happening in the financial services, is many new technology players coming and forming alliances with other technology players. And probably a lot of you have heard of fintech sector, where many new fintech players are offering better services than the old vertical model. So we've undertook a study to see how machine learning can be used in this big ecosystem. And we decided not only to look at the literature, but also talk to practitioners and do interviews. So we've done that. So this paper is a results of what we have discovered so far. So we looked at the literature, and it's almost clustered into 3 areas: finding patterns in the data, information processing, analysis, and trading decision making. This is probably what is the most familiar to computer scientists. You look at financial data, you look at stock price movements, and you try to do things like predicting stock price and do better than statistical techniques. And it has obviously advantages to use machine learning in this area. And you can use it for asset categorization, pricing, derivatives. And of course, as you move into high frequency data, you can apply it to find out about intraday patterns. But there are other areas which are probably not obvious that use machine learning. One I would say is information processing and analysis. Machine learning assumes that the data is clean, and you know, you have everything is well organized, but far from it. One of the challenges is low-level nature of data, and you have structured, unstructured, multiple sources, and having country data from different countries means that there is different semantic content. So you can't really feed the data straight away into ML boxes. There has to be processing. And in this space, you can use ML to process the data so that it can be fed in, not necessarily ML, it could be fed in ML or in traditional boxes. Then another area which is more machine learning is not used in isolation. It's part of a whole workflow and a process which involves decision making. And this decision making has become very complex, because you make an investment decision, and that investment decision is going to go through multiple stages to be converted into a trading decision. And all along this big chain of decisions, you have to make sure that the original goals are preserved. So you can use a machine learning way down the chain, but how does this machine learning knows about the original goals? So that's more looking at the entire process rather than just analyzing the data. And there has been evidence from practice that machine learning has improved this robustness of automatic trading system, but we haven't, I mean, from the academic literature, I haven't seen much of that. So there are suggestions that it happened in practice, but as I said before, most of the literature tend to be more on analyzing data patterns. just examples, you have algorithms that can choose assets for trading, or you can have algorithms that can take charge of a trading strategy. You can have algorithms that can look at existing trading strategies, and based on the data, they can improve them. And then you have algorithms that can create algorithms for trading. So in the level of innovation um, in how to apply machine learning technology is fairly diverse in this space. And obviously, practice is a bit ahead of, I would say, academia. So there is plenty of opportunities to have research studies in this space. So what I believe research areas will be really focus on information representation for machine learning powered analytics, because again, you know, how do you convert low-level data from different sources in high frequency with high degree of noise into quality data that could be used within machine learning? Then within the machine learning themselves, more sophisticated techniques using the latest techniques like deep learning, and then the automating the entire workflow. You know, how do you relate different performance measures from the investment down to the trading decisions? So there's plenty to do in the future based on the results of this study. So what's next? We want to reach out to more practitioners to see, you know, refine the results that we got. So all these results are in a paper, which I'm happy to share. I think it's available through the link to this seminar. And also, we want to engage more into doing research for how to apply machine learning in electronic trading, because it falls between the cracks. You need people who not only know about machine learning, but software engineering, because you need to put machine learning in the context of trading, but also in finance area, because the measures, the models that you're competing with are traditional financial measures. So if you do machine learning, how does it compare to the traditional model? Or in many cases, you have the traditional model coexisting with machine learning, and how do you do that? Yeah, so we also, again, very keen to have multidisciplinary collaborations between academics here at UNSW in both computing and finance and industry, guided by the insights of this study. And I think that concludes my talk. And thanks to the sponsors of this project and the people in industry who gave us a lot of information and helped us with the study. Thank you.
Thank you very much, Fethi. I'm going to take my privilege as the host of this meeting to ask a question for you. How do you deal with black swans? I mean, that's a sort of, black swans are the sort of thing that machine learning is pretty bad at, because by very definition of it being a black swan, we don't have any data.
So what we have in the survey, we ask we ask the respondents two things. One is, how do you manage risk? So there are management. So within the governance of ML, there are mechanisms to basically deal with unexpected events. And then within the machine learning themselves, we ask them, how do you deal with the you know, how do you make sure, you know, how mitigate your risk? And nearly all of them, they've mentioned having a human in the loop. So far, the human seems to be the main risk management strategy for these companies that we talk to.
Thank you very much, Fethi.
No
We're now
problem.
going to move to one of our rising stars, Scientia fellow Lina Zhao, who's going to tell us about her NeurIPS paper on the application of machine learning. So, Lina, over to you.
Thank you, Toby. Thank you so much. So can you see my screen?
Yeah, we can see your
Thank
screen.
you. Wonderful. Thank you so much. Okay. Yeah, it's a great pleasure to be here today. So AI for quite some time now has transcended its theoretical existence in universities and research institutions to make waves across the different sectors of our daily lives. And to a larger extent, AI has succeeded in its endeavors, actually. And most of us today may not be fully aware that how AI is transforming the transportation. So the AI advances have helped the transportation sector progress in its journey of innovation and evolution. Leveraging AI in transportation can help to improve the traffic congestion, enhance the shortage of the public transportation services, lessen the carbon emission, better management of the traffic accidents, increase the passenger safety, and optimize the transportation planning for minimizing the overall financial expenses. And not to mention the autonomous self-driving cars, the concept that was once merely a sci-fi fantasy has now become a practical reality. So today, I'm going to have a quick introduction on one of our recent progress in the line of AI in transportation, in particular on traffic prediction, adaptive graph convolutional recurrent neural networks for traffic forecasting. This paper is accepted by the Neuro IPS this year. So the traffic forecasting aims at predicting the future status, for example, the traffic flow, traffic speed, and the passenger demand of the urban traffic systems. It plays a vital role in traffic scheduling and management, delay prediction, and the road planning. So as such, accurate learning the complex spatial and temporal correlations in the time series data is indispensable for understanding the traffic dynamics and predicting the future status of an evolving traffic system. So this area has been extensively researched in the past decades. In recent years, graph neural networks based approaches have been testified as a promising solution. So the existing works more focus on designing the complicated graph neural network architectures to capture the shared patterns with the help of the manual domain-specific engineering. In this paper, we propose a novel graph neural network solution by adaptively learning the robust, transferable, and generalizable patterns without any human intervention. So first, we designed two adaptive modules under the framework of the graph neural network for the traffic forecasting tasks especially. So the first module is node adaptive parameter learning. It is to learn the node-specific patterns for each traffic series and factorizes the parameters in traditional GCN and generates the node-specific parameters from a weight pool and the bias pool shared across all the nodes according to the node embedding. Another module is a data adaptive graph generation module. It is to infer the node embedding with attributes from the data and to generate a graph during the training stage. So these two proposed modules are independent and can be adapted and plugged into any existing GCN or GNN-based traffic forecasting models, both separately and jointly. So all the parameters in the modules can be easily learned in an end-to-end manner. Furthermore, we combine these two modules with recurrent networks and propose a unified forecasting model named Adaptive Graph Convolutional Recurrent Neural Network, AGCRN. So it can capture the fine-grained node-specific spatial and temporal correlations in the traffic series and unify the node embeddings in a revised GCNs with the embedding. So the core idea behind it is replacing the fully connected layer in RNN with our proposed adaptive GNN architecture. So given the original first order Chebyshev GCN in the equation shown in the equation 1, we propose the node adaptive parameter learning enhanced GCN in equation 2 by decomposing the parameters to a node embedding matrix and a parameter pool. We also propose the data adaptive graph generation enhanced GCN shown in the equation 3 by learning the spatial dependencies from the learnable node embedding matrix. So through constraining the node embedding matrix in equation 2 and equation 3 in the last slide, so we can get the final formulation of our proposed model. As such, training this model can result in a meaningful node representation vector for each traffic series source. For example, the roads for traffic speed or flow, stations regions for passenger demand. So the learned node representation contains the valuable information about the road region and some associated semantic high-level information, and also can be potentially applied to a broader range of tasks. So just briefly report partial results based on our model. So we validate our method on 2 real-world traffic benchmark data sets collected from the ProMS system and conduct the multi-step traffic forecasting task, which predict the future 12 steps traffic based on the previous available 12 steps data. So we compare our model with a set of state-of-the-art, and you can easily observe from the table. So our model actually achieves significant improvements. So more detailed results and the technical details can refer to our paper, which has been online available. So in general, our work this work present in this paper enables more accurate and generalizable learning of the time series data in the context of the traffic forecasting, which facilitates the higher level traffic scheduling, such as the taxi dispatch and the road planning, something like this. And in this way, our work can help save time for travelers, improve efficiency and income for the transportation operators, and save the energy consumption. In a broad sense, so we provide actually a promising solution for the adaptability. So it is desirable in the correlated time series analysis for the broader social and business applications. So the proposed adaptive modules enable the elevated robustness of the data analysis and the relevant applications based on the dynamic, interdependent, and time series data. So the research generally supports the better modeling and analysis of multiple channels of data based on the graph structures with the complex explicit and implicit correlations. So our model has the implications and potentially accelerates the research progress in address many world-scale economic and societal issues that rely on the complex time series data. For example, the predictions of influenza outbreak, the economic growth, and the climate change. Yeah, thank you very much.
Thank you, Lina.
Yeah, under 10 minutes.
Thank you.
Okay.
Can I'll ask a quick question just before we move on quickly to the next talk, which is that
Sure.
traffic behaves at different timescales and so on. How do your models capture the different timescales and granularity that you see within a phenomenon like traffic?
We leverage the typical time series data, as well as we also incorporating some high-level semantic information. So kind of like the model map them into the graph structure. So and also build up the correlation, the connections between each entities on the graph. Yeah. So and then we present graph embedding techniques to learn the robust and the reusable patterns. So these reusable patterns can contribute to some other tasks because it has a good generalization ability. Yeah.
Great. Thank you very much.
Yeah, thank you very much.
So we're going to move on. We're going to stay with machine learning. We're going to move now to one of our other Scientia fellows and a future fellow herself, another rising star within the school. Yang Song's going to tell us about her work on using machine learning for analyzing microscopy images. Over to you, Yang.
Okay. Okay. Thanks, Toby. Can you see my slides?
Yeah, I can see your slides.
Okay, that's great. Okay, so my talk is on unsupervised instance segmentation in microscopic images. So it's based on our paper in CVPR this year. And so I'll start with some background information about what is cell nuclei segmentation in histopathology images. So as you can see in these images, these are very typical histopathology images. So what we want to do is we want to segment the cell nuclei. So those are the blue, dark blue blobs in those images. So there's some very difficult problems in this kind of issues. So the first one is for many images, we can see there's some overlapping cells or they're touching each other. So our objective is we need to separate those cells and be able to segment them individually. And there are some other structures in the image that actually look very similar to cells. For example, some are mitosis, and those will be special structures in the images that we do not want to confuse with the cell nuclei. And there's some other more general challenges, like the images all look very different from each other, and the boundary of the cells are very obscure. So how do we segment these cells? This is actually a very basic problem in biomedical imaging, and it has been studied for many years. But accuracy so far is still quite low, around 80% accuracy. So normally what we do is we just develop some fully supervised segmentation models based on deep learning. So right now for segmentation, either we do something similar to Mars RCNN or UNet models. So those are very popular models, and these are some other our previous work in this area. So we got some state-of-the-art results for fully supervised segmentation. And so what we consider more interesting is what if we consider unsupervised segmentation. So that means we have the histopathology images, and we do have the segmentation ground truth, but we don't want to use this ground truth for training the model, but instead we just use the ground truth for evaluation. And so in order to have a better performance rather than pure unsupervised segmentation, we try to use some supervised information from fluorescence microscopy images. So what we want to do is we want to train a model based on the fluorescence microscopy images, and then we'll adapt this model to histopathology images and see how it works on histopathology images. So why we want to do this is because it's very easy to see the cells from fluorescence microscopy images. So that means it will be much easier to obtain annotations for fluorescence microscopy images. And then because deep learning requires lots of data, so if we use annotations from fluorescence microscopy images, then we can expect that we get better performance because we are able to get more annotations for fluorescence microscopy images. So overall, we have a reduced effort for this method development because it's much easier to get annotations for fluorescence microscopy images. So, but the difficulty here is because these two domains look very different. So we can't just train the model on fluorescence microscopy image and simply apply it to histopathology images. So that's where this unsupervised domain adaptation comes. So what we mean by unsupervised domain adaptation is we train the model for fluorescence microscopy images, and then we do domain adaptation to adapt this model to histopathology images. And so this diagram here shows our overall structure. So the method works by, initially we have the fluorescence microscopy image, and then we have the cyclogen and nuclei implanting step to generate some synthesized histopathology images based on the fluorescence microscopy images. And then once we have the synthesized images, we can then do another segmentation model training to get a good segmentation model that can be applied to the histopathology images. So what's more difficult here is we can't just do a training using the synthesized images. Because the synthesized images, although they look very similar to histopathology images, but there are some very obvious difference in terms of the overall appearance. So if we use these synthesized images as the input image to train the segmentation model, we will get some biased performance that so the model would work well on the synthesized images, but not really well on the real histopathology images. So how do we deal with this problem is by this design of the PDAM model. So in this model, I don't really have the time to go into the details, but essentially what we do here, the most important component is the semantic branch. So this branch helps the model to learn features that actually represent the real histopathology images. So the overall segmentation will be optimized towards a good performance for the real histopathology images, even though we don't have the ground truth segmentation for those images. And also we have some other image adaptation, instance adaptation, and semantic adaptation modules. That's for the adversarial learning of the domain difference. So that's a very brief overview of our method. And then for experiments, we tested on 2 histopathology image datasets with just one source dataset for the domain adaptation. And here are some numerical results. So we got better performance than the other state-of-the-art UDA methods. And what's more interesting is our results actually show improved performance even when compared to fully supervised methods, especially for the unseen dataset. So the unseen dataset means we don't have this type of organs in the training set. So because the images would look quite different across different organs, so we keep some organ image from certain organs as a holdout set, and then evaluated that set. So with this domain adaptation, we can get better performance on this type of unseen datasets. So that's in conclusion, we have presented the first UDA instance segmentation method, and we evaluated on 2 histopathology image datasets. And so currently we are trying to improve these UDA methods with feature disentanglement. So that's some other further improvement we can develop into the method. And also we consider how we can do weakly supervised segmentation. So instead of pixel-wise annotations, we try to just use a single point as the annotation per cell nucleus. So that will also reduce the number of annotations that require to train the model. And we just submitted a conference paper just now. So, okay, so that's all from me. Thanks.
Great, thank you very much. I'm going to ask a really quick question.
Yeah.
We're pressed for time, which is how good are we compared yet to human pathologists at doing these segmentation tasks? So how soon before human pathologists can say we didn't like doing that any rate, now we get the computer just to do it?
quite difficult to see for segmentation results because there's no large scale evaluation for this type of problems. But now if we consider classification problems for tumor histopathology images, actually deep learning does outperform pathologists. But that's based on some very large data set for training. And also in the evaluation, there's probably some bias. In normal data sets, we wouldn't really include those very unusual cases. But then pathologists would do well with those unusual cases.
It's the usual problem with deep learning. If everyone the data, you're okay, but where we don't, we're in trouble.
Yeah, that's true.
Thank you very much.
Thanks, Toby.
We're going to have to move on.
We're
behind schedule as usual.
Share. Okay.
Thank you. Now we're going to move to one of our great PhD students, Annette Spooner, is going to talk about some ensemble methods. Annette, over to you. Annette.
Sorry about that.
There you go. You should be unmuted now. Great.
You're right. Okay. Hi, everyone. My work in AI at UNSW involves building machine learning models to predict the onset of dementia. Currently, the cause of Alzheimer's disease is not known, nor is there any cure. So these models are searching for new knowledge and, in particular, aiming to identify risk factors for dementia. Hang on. Oops. So real-world clinical data presents many challenges to machine learning, not the least of which is that it's typically high-dimensional with a small number of samples. So, of course, we can apply feature selection to reduce the dimensionality of the data. And feature selection, as we know, involves finding the smallest set of features that allows accurate prediction from the data. Now, from a clinical perspective, feature selection can improve understanding of a disease by identifying important factors at play in that disease. And this can in turn produce more interpretable models for clinicians and lead to more cost-effective procedures for identifying patients at risk due to a small number of tests being required. But the problem with building models from high-dimensional data with low sample sizes is that they tend to have high variance. And clinicians won't have confidence in our models if they return different results each time they run on new data. So in knowledge discovery in particular, reproducibility is of the utmost importance. I'm sure we're all familiar with the concept of ensembles of classifiers and the techniques of bagging, boosting, and stacking. But this technique can also be applied to feature selectors to reduce variance. To implement this, we first take a large number of bootstrap samples from the training data, say 50, and we run the same filter or feature selector on each sample. That gives us 50 different ordered rankings of the features, or 50 different feature subsets, depending on which feature selector is used. Each one might be slightly different, but of course there'll be some similarities between them. And the more relevant a feature is, the more likely it will be ranked highly by the feature selector. Then we aggregate those rankings from the individual feature sets in various ways. So for example, we might take the mean of the rankings from the individual feature set, or we might count the number of times a feature is included in a feature subset. Then we rank the final feature set by those aggregated values and apply a threshold before training our model on the aggregated feature set. Now that threshold, which separates the important features from the redundant ones, can be a simple fixed threshold, such as the top 1% or the top 5% of the ranked features. But you can imagine that if you have a genomic data set with possibly tens of thousands of features versus a data set from a clinical study with only a few hundred features, then a fixed threshold of say 1% will return a vastly different number of features for those two data sets. So a fixed threshold must be carefully selected and requires knowledge of the data set. But I've been working on developing an automatic threshold that can adapt to the data set at hand. So what we see here is a graph of the aggregated values for each feature after applying an ensemble feature select. Now, it really doesn't matter which feature selector or which aggregator we use, we can plot a graph like this. And you can see that at certain points, the values drop away sharply. These points can be used to group the features into similar levels of importance, and we can find these groupings quite easily by applying a one-dimensional k-means clustering. then the features in the first cluster are the most important ones. And this eliminates the need to select a threshold. Then we can measure the stability or the reproducibility of the features selected by comparing the final sets of features of selected features from each iteration of a 5-fold cross-validation. So here are some results from one of the 12 feature selectors that I studied, and this one's a univariate model score. So the dark blue bar on the left of each group shows the stability of the individual feature selector without any ensembling. The other coloured bars show the results of show the stability using ensembling with different aggregators. And each group of bars represents a different threshold. So I've used 5 different fixed thresholds, and then the last bar is the automatic thresholding that I just described. So as you can see, in each case, the stability improves using the ensembling method, and the automatic threshold achieves stability that is comparable to or better than some of the fixed thresholds. And similar results can be seen in the other feature selectors studied. At the same time, we can see that there's no loss of performance in terms of model accuracy. And in many cases, the performance of the ensembles is slightly better than that of the individual methods. Earlier this year, the Lancet Commission on Dementia Prevention, Intervention and Care released an updated list of the most important modifiable risk factors for dementia. These are shown on the left. On the right are the predictors selected by our models using this ensembling technique. Those in bold are the ones that are the same in both lists. You'll notice that many of the predictors that our models are identifying are also on the Lancet list. Most are in the late life section, but that's because the data we have is only from participants aged 70 years and over. Of the other factors identified, age is known to be the most important predictor of dementia. The loss of the sense of smell has been identified in the literature as a predictor of dementia. And the new, oh, sorry, what happened? Sorry. And the neuropsychological test scores are directly measuring cognitive function. So you would expect them to be highly predictive. So there's a bit more work to do to collect data from early and midlife participants and fine tune these models, but the methods are looking promising. Thank you.
Thank you very much. We're running short of time, but let me ask a question at any rate, before we move on. So,
Sure.
are you thinking of applying these methods to other types of data beyond Alzheimer's, or?
Yes, it's certainly possible, and probably to compare my methods to in other data sets, I will have to do that. But my main focus is on Alzheimer's.
Right. Well, it's a fantastic problem, and wonderful to see people looking at it.
Thank
Great.
you.
We're moving on now. We're the final talk before we're going to have another break. We're going to hear from Yoann Buratti, who's another one of our fantastic PhD students, talking about an application of AI to an area again that UNSW, of course, has lots of expertise in, which is in solar cell setting. Over to you, Yoann.
Like when you start sharing, the mute button is hidden. All right, thanks, Toby. So my name is Yoann. I'm from the School of Photovoltaic and Renewable Energy Engineering. And I'm going to talk to you today about how we use machine learning and artificial intelligence to make better solar cell. So I will have just a slide overview of a few topics I'm working on as part of my PhD. And please contact us if you want more information or would like to learn more about what we do in our group. The first one is going to focus on how we make solar cells, so the production line using solar cell. And it's very important for production to have a very good efficiency in the solar cell. Like it's the single target that we're trying to achieve is higher efficiency, because a higher efficiency at the same cost is just scales so rapidly when you're installing mega or gigawatts of solar. So when you're optimizing this production line, usually what is done is a process-wise optimization. So you have different steps where you're looking at, maybe you're cutting the cells or you're doing some deposition or some metallization. But because there's so many processes, it's really hard, or so many parameters in the process, it's really hard to capture the interaction of those processes. And so what we're trying to do here is to enable machine learning to learn those relationships within process parameters and output efficiencies to then optimize the efficiency of the production line. So for that, we have different recipes, so different parameters of the different processes in the manufacturing line. And by looking at the natural variation of that production line, it naturally generates a distribution of efficiencies. And we're going to use neural network to learn the relationship between those parameters from the recipe to the distribution. And once we have that, we can pass it. So now we have a model, a function that can output the efficiency. So we can look at this function with a genetic algorithm to find what is the local optimum of that function when you're trained on that distribution. And so you get a better recipe. So you can input your new parameters, you still have some variation, so you get a new distribution, and you can basically repeat that. So our neural network works really well in terms of just predicting the efficiency of the line. But the interesting thing is by looping this neural network with a genetic algorithm that's going to increase the efficiency when we're comparing predicted and actual, we're going to get a new distribution with higher efficiency, and we can repeat this process a few times. And we show here that we can increase the efficiency from 18 to 19.5%, but it maybe doesn't talk to you much, but having worked in a solo company, increasing by even by 0.01% is something people work on because when you scale it to megawatts, gigawatts, it's actually a lot of money. So this is like the application on solar cell manufacturing, but you can see that it could be easily transferable to other types of manufacturing. Secondly, still a bit linked to the manufacturing, I'm going to talk to you about a bit electroluminescence images. So a solar cell converts light into electricity. But interestingly, you can also give it electricity and it will shine light. And if you capture that light, you get those kind of images that we call electricity luminescence images. And in the factory, when you're producing the solar cell, it's very important to make sure that the solar cells are bent towards the same type of electrical parameters, which usually we use current voltage testers, because when we're building solar modules, so we put a lot of cells together, so that's the one usually installed on your roof, you want to have similar quality of solar cell, kind of how you build processors out of transistors, right? You have your i3, i5, i7. So same idea here. And so what we want to do is use this electroluminescence image as a replacement for those IV tester for binning in manufacturing line. And the reason is mostly because it's faster and cheaper, but it also provides information on the luminescence images that has defects that can help troubleshoot the production line. So for that, we have a deep learning framework, so CNN, convolutional neural network, that will learn how to bin those cells in terms of efficiency, so supervised learning. And we added to this first classification step, just a second regression step where now that we have trained on enough data, the CNN learns what are the important features that you can see that actually impacts the efficiency of the cell. And then we can apply that as a feature extractor, so freeze the CNN and then just extract the features to train a machine learning regressor, like a random forest, to train the efficiency of the cell if you want more precision on your efficiency data. So as you know, probably CNN works very well in classification problems, and we get very good accuracy in predicting those reject cells and those efficiency bin. And when we pass it to the second step, we even have a finer prediction of the efficiency when we compare actual versus predicted. And this opens up actually because UNSW has a lot of different industry partner to train on multiple different data sets of different architecture, different types of solar cell, to kind of build an equivalent of an image net for solar cell that could be used and deployed in the manufacturing. The final topic I want to talk to you about is diving a bit deeper into the physics of the solar cell. So we'll see who has taken device physics here, but I'll try to give a top level overview. So when we have light that hits our solar cell, the photon energy is carried over to an electron that gets excited, and we try to extract this electron before it relaxes down to its original energy. And that's basically the photovoltaic effect. And when you have, how long can you keep this electron excited is what's called the lifetime of your electron. And when you have defects in your solar cell, they impact this lifetime. And the way they impact it is driven by this Shockley-Rithold equation. So we have a physical model on how defects, which have defect parameters, impact the lifetime and ultimately the efficiency of the cell. So extracting those defect parameters is important to understand what type of defect it is. If it's like a copper, iron, or other kind of impurities that whistle their way into our solar cells when we make them. And the extraction of the defect parameter is a complicated process and it's very manual. So what we want to do here is use machine learning to learn the reverse function, the inverse function of the Shockley-Rithold equation under certain conditions. So for that, since we have the equation, we can simulate a lot of different curves from a lot of different random defect parameters, which will explore the entirety of what we think is a defect parameter space. And then we can predict back those two defect parameters here. Example, I show two parameters, ET and K, without going into much details, with good R square. But interestingly enough, we have actually artifacts on those prediction, which can be linked to the physics of the Shockley-Rithold physics. And for example, here the 0, 0 value is like a very interesting shape for machine learning scientists where something's happening, but when you're looking at the curve and what you're generating with your Shockley-Rithold equation, you can see that it is very hard manually to tell the difference, and the machine learning is still able to like get most of it right. And now that we train this on simulated wafers, it's interesting to apply it to actual data. And on the graph on the right here, we measure at different temperatures, which are represented by the different color of the different curves. And each line in the curve represents the combination of the two parameters that are potential solution of this Shockley-Rithold equation. So for one temperature, there's infinite solution, but if you have multiple temperatures, you're going to look at the intersection of those different solution space and look for what the intersection is. The problem is when you measure, you have noise, so the intersection is never really well defined. And that's where machine learning can help also address this noise issue. And here we show that we have very good result compared to what the manual approach looks like. Yep, so this is the overview of what I'm doing here. If you're interested to learn more, take a quick screenshot, send me an email or go check out our group's website. And so just look for ACDC UNSW in Google and you'll find us. And we're delighted to have the opportunity to talk. Thank you, Toby.
Great, thank you very much. Well, again, we're running late. It's time for us to take our next break, but I'm going to throw in one quick question, which is, how did you get excited by machine learning?
Oh, so actually, that's an interesting one. I have a very math background I studied in France and actually went to Stanford for my master, where I stumbled upon Andrew's class. Yeah, and that got me into it. Yeah.
Great, très bien, très bien.
Thank you.